So the purpose of these events is to provide you with a bit more information about the challenges that we have set out to solve in the extension of the ORCA Hub. Hopefully you all managed to attend the webinar that we held on the 17th of June, and at that you got a flavour of what we've achieved so far and what we're planning to do next. This morning you're going to hear from Professor Mirko Kovac, one of the ORCA Hub's academic leads, about how he and his team will work on aerial robot inspection of large infrastructure in challenging conditions. So Mirko will present for about 20 minutes before we will open the floor to questions. Please add your questions throughout the chat, in the chat throughout the presentation, and we'll address as many of them as we can do at the end. Any that we don't get to, we'll respond to after in a follow-up email. So just before I pass over to Mirko, following this event and the others this week, we're going to be hosting a series of what's called AIM days in the first 2 weeks of August. And we'll be having one AIM day for each of the challenges that we've set ourselves. So the purpose of these AIMS days is to give you an opportunity to speak one-to-one with the academics leading the work, to discuss working on projects together related to their challenge. So if after hearing today's session, you're interested in discussing a project idea you have with us, please get in touch with me at my email, which I'll shortly put in the chat, and I'll send you a pro forma to complete to outline your idea. We'll then use this to plan and prepare for our AIM day one-to-one with you. So you can see the times and dates of the AIM days on the slide just there. I'll also post these in the chat shortly too, and we'll also add these to our website and social media channels with details about how to get involved. So I think that's enough for me just now. I'm going to pass over to Mirko.
Thank you very much, David. Hi, everyone. It is my great pleasure to welcome you today, to see you today. Apologies again for the slight delay. We had some connection issues here, and apologies also for my mask, which doesn't make it easier to see the facial expressions, but I hope that the voice is clear enough and the slides and the technology should speak more than my face, I think. So the goal of our challenge 2 is to look at aerial systems that can inspect large infrastructures with the goal to create a sensor placement methodology that can interact with the surface and like this get insights onto the blade surface, wind turbine blade surface, as well as the tower and the nacelle. Now for that, we really want to combine a variety of assessment and inspection techniques to create a 4D framework. Now 4D, what does it mean? What do we mean by 4D and why is it important? So 4D it is because we want to not just map the outsides, which is something that is typically done with drones, where drones would fly, they would take pictures or they would map the surface and then like this get operational insights and be able to optimize maintenance schedules and reduce downtime. And this is something that is already used quite a lot and is used routinely as a way to inspect wind turbine blades. Now, what is missing in today's technology in that way is that the knowledge on the surface, the knowledge on the materials, and the knowledge on the insides of the blades is not there. So the data is not there. And because of the lack of this data, a lot of manual techniques are still being employed. So the manual techniques, for example, include upsiling, so people that will climb up and down the wind turbine blades, or longer downtimes of the facilities, or people that will go inside of the blades to inspect the different aspects of it. And like this would be very costly, dangerous, and also not provide the data that is needed to get insights onto the operations. Now, one particular use case that we are looking at is the leading edge, and there's a lot of potential for leading edge damages on the wind turbine blades, as well as the lightning protection system, so the LPS. Now, the LPS is something that happens at the tip of the blade, and it's really important to see whether this LPS system has been damaged by lightning or not. And this is typically, again, done by manual interventions, by manual people downsiling or climbing on the blade and looking and measuring the resistances. So we have methods how to do that in a robotic way with much faster assessment techniques and much faster ways to do this. Another use case, the use case number 3. So the first is the blade, the leading edge. The second is the LPS system. The third one is the insides of the blade. So here in this picture, you see the inside of a blade. And these are inaccessible, highly complex environments where it's really difficult to actually get insights and connect and map the insides of these blades. So for this, we use small palm-sized drones that can go inside and create 3D maps of the environment to get insights and like this, be able to assess damages. Okay, so these are, let's say, 3 use cases that we can focus on in the first instance. Now, another area that is also linked to that is the way how to connect or how to place sensors onto those infrastructure elements. And we have techniques of aerial robots, as you see here, that can attach those sensors or that can perch to the surface and then do the physical interaction with the surface. Now, this allows the robots to do NDE measurements, which means to measure, for example, the thickness of steel plates or the tower, or use radar technology like this to assess the structural integrity of the composite structures of the blade, or also place those type of limpet sensors, which you might have come across from the ORCA Hub, where we can measure vibration or create communications, communication frameworks and IoT kind of techniques to get insights onto vibration and other parameters on the facility. So another example here that we also have as a technical capability is on 3D mapping and localization. So you see here in the top left a multi-level, multi-resolution or multi-level resolution framework that uses various ways how to combine LiDAR vision and onboard odometry to create 3-dimensional maps of the environment that then can be used for the robots to navigate in successfully. So this is something that also we have been integrating and that we are now testing on these wind turbine blades. So at the bottom right, you see this, what I mentioned before, which is the very small robots that can fly inside of the blade and like this map the insides. So just one small video here. And basically it flies relatively slowly, but that's on purpose. It could fly faster. And the main key here is that it uses insect-inspired vision. So it uses optic flow-based navigation to avoid the obstacles and follow the path or follow the wall. Now, this type of insect-inspired vision can be done on an extremely lightweight and extremely small aerial platform. So at a weight of only about 20 grams of electronics, including battery, we're able to do full autonomous navigation in those very complex environments. And this is something that's quite powerful and that we also can use in pipelines or in other constrained environments, in tunnels or anywhere where it's difficult to assess the structures. Right, then how does it all come together? So we have these different techniques. We have the sensors, we have the aerial robots, we can map the outsides of the blades, the insides of the blades, we can get non-destructive evaluation of the blade itself. And so what about linking this into the operational tissue, the digital tissue of the wind turbine facility, and how can we link it to the digital tissue of the ecosystem of the different robots that interact with the blade? So the flying robots that would then coordinate ground or underwater robots to create the data, collect the data, and like this, all these data sets from the various levels of robots would feed into a centralized artificial intelligence systems for the digitalization of those wind turbines. And this is here what we focus on, this, on the validation and overall system that can fit it all together. So I hope this was a little bit informative. It's very short, but it's short on purpose because I would like to more hear your opinion, your feedback, and discuss more directly with you of how this can address your operational needs. So thank you very much.
Are there any questions from any of the audience this morning? I've not seen any come through the chat so far. If not, I guess I'll get one kicked off for you, Mirko. So as an industry-driven project, we're obviously eager to get the support and input and direction from industry. So what would you like to see in terms of support from industry that would help you for this?
Great, thank you. That's a very important question. I think the two things come to mind immediately. Number one is teaming up on a case study. So we have these case studies, let's say inside of the blade flying or the inspection of the leading, this lightning protection system or the drain hole on the blade. So teaming up and labeling the case study to do it together, which has an effect of publicity and labeling. So it's really partnering on that, but also really using the facility of the industrial partners to really validate the technology. So that's number one, and this is very valuable, and we're very keen for that. The second one is to also just identify the cost proposition. So how much is this worth? Because if you have a capability, and we have a lot of capabilities, but if you can put a number on it, this will be like a springboard for commercialization, for going through the commercialization route of the universities. And these numbers are extremely valuable so that we can benchmark the kind of overall proposition and value of the technology.
Great, thanks, Mirko. So we've had a couple of questions in the chat there, so I'll just read the first one out. So how close are the key technologies to being able to pilot some of these things that you presented today?
So ORCA is in its latest year. So we have another like 8 or 9 months left within the main ORCA framework. We then have extensions as well that we look at. But ORCA in that way is very mature. So we are ready for piloting now. So it's really now defining which use cases we want to team up with and making a schedule in the next, with a horizon of a few months to do the tests together on the real facility. This will validate technology, it will showcase a new capability, and it will put the foundations for joint projects and funded projects for next year. So in a nutshell, it's basically now, it's just about teaming up in the right way.
Perfect. And we've got another question here from Oliver. So how does the drone cope in different wind conditions when external to the structure? And what type of control theory are you using? And then there's a follow-on question there as well. And how does the disturbance affect the sensor data when merging the data?
Great. Thank you very much for this question. That's exactly what we are studying. And so we have here on the top right, you see the wind direction, and you see the kind of expected turbulence around the blade or around the infrastructure. So depending on where you fly and where the wind is from, we can model the turbulence levels to some extent, or model the type of disturbance that it might experience. Now, one approach to make it more wind robust is this perching method, as you see here. I think you see my mouse, right? So you see here, it flies, it attaches an anchor, and then can perch down like this. Now, this tensile anchoring is really helpful because it constrains the motion in one direction. And we can then apply a force and like this greatly stabilize the platform, even during windy conditions. We have characterized this in a laboratory environment in different wind conditions, and it can work quite robustly. The control theory that we use is admittance control, which means to model the environmental interaction as a spring damper system, which can then be linked into the autonomy of the vehicle to do certain missions while interacting with the surface. The sensor data linking together is this NDE sensor data, as you see here, for example. This would then go into a digital model of the blade, the 4D model, similar to the BIM, the Building Information Management or model, which is like a digital self of the platform or of the facility. So we would frame this into database and together so that it's all available for the user.
So I've got another question, which you have touched on already, but just maybe just to clarify a bit further. So how is your challenge going to interact with the other work that's going on in ORCA, and how does it all kind of interlink with the other research that's going on?
Right. So this challenge is really focused on the aerial part, so everything flying, and this can be used, as explained here, in wind turbine blades, but it's also for oil and gas, it's also for pipelines, it's also for factory environments or buildings even. So it's really like a sector agnostic capability, if you want. So in that sense, we'll also engage with the stream B of ORCA, which looks into the building sector, construction sector, bridges, dams, storage tanks. So it will have a sector transition as well over the next few months. But also we then link together with the ground vehicles and walking robots, where we can, for example, have the robots take off from a ground vehicle, interact, sense, and then come back to the ground vehicle. So this type of works we are already doing. And we're linking it also together with virtual reality frameworks, where we can do all of those remotely. So on a distance of hundreds of kilometers to operate the robots without being on site at all.
Perfect, thanks, Mirko. So if there's no other questions from the audience, then I guess we can draw to a close. If there are any questions that come after today, please feel free to email me. I posted my email in the chat. Also remember that Mirko's AIM Day is going to be on the 13th of August between 9:30 and 1 o'clock. So if you're interested in being involved in this particular ORCA challenge, please get in touch with me and we'll pick up discussions from there, and I'll talk about how we can get involved. So if there's no other questions at all, thank you very much, Mirko, for your presentation. Thank you for the questions, and thank you everybody for attending, and looking forward to engaging with you in the future.
Thank you. Same for me. Thanks a lot for being here and being part of this exciting project.